Okay, camera ran out of space. Just the right point. We're going to move on to our kind of our last discussion for today, which is on this. Well, we got one more tiny discussion at the end, but one of the other things that we said was a major factor that affects the weather, particularly the part that affects the wind the most. Do you guys remember what it was? Those first three things at the very beginning of the lecture today that we talked about? There's one in particular that affects the winds. You can go back and look at your notes, see if you wrote that down. What were the three, tell me this, what were the three big things that affect the weather, did we say at the beginning?
Thermal energy.
Thermal energy.
Uneven distribution.
Yep.
And water vapor in the atmosphere.
That's right. So of those three, which one was connected the most with the wind? Did you write that down?
Uneven distribution.
Yeah, the uneven distribution of thermal energy was what affects the wind the most, right? So that's what we're going to talk about now. And of course, this is going to be a big discussion on how wind works. Why is it windy one day and not windy the next? Why are winds really high one day and just kind of a nice gentle breeze on other days? Why does it seem like you always have wind at the beach? Things like that. So let's discuss wind. The temp differences between the equator and the poles causes wind. The cause, you probably have already heard this, but just make sure you know it. Hot air rises. Have you guys heard that before? Yeah? If you have a two-story, do you guys have a two-story house, either of you? Yeah, yours is 2 stories, yours 2 stories as well. So have you ever noticed that it tends to be hotter on the second level than it is on the first level? Or it can be? So you could set, it always feels warmer when you go upstairs. The AC unit that we always have issues with is the upstairs one because it's just harder to keep that area cool during the really hot summer months because that's where all the hot air accumulates up there. And the AC unit upstairs is making cold air, but the cold air doesn't stay up there. It sinks down here and actually helps cool the lower level, right? So the fact that hot air rises and cool air sinks affects the pressure, the air pressure, and these differences cause the winds. Now, when I say the temperature differences between the equator and the poles, what are the temperatures like at the equator versus the poles? The poles, what do we think of when we think about the North Pole and the South Pole? What's the temperature like there?
Cold.
It's always cold, right? And then when you think about the equator, right? Like when you think about getting down close to the equator, like when you go to the, do you guys say Caribbean or Caribbean? Which one would you use? Is it Pirates of the Caribbean or Pirates of the Caribbean?
Caribbean.
I would agree, all right? So in the Caribbean, you're close to the equator, and so the weather's generally warm there, right? So we've got all this warm air that accumulates around the equator and all this cold air that stays where the poles are. And that again has to do with the tilt of the Earth, because if you look at the poles, if you consider the poles with the tilt, right, it doesn't matter. Like if it's tilted like this towards the sun, southern hemisphere is getting more sun, but the pole's still hidden down here, right? It's still not getting much. It's still further away. Same thing here, when it rotates back this way and the northern hemisphere is closer, this pole is still further away because of the curvature of the Earth, right? So those regions tend to stay cool. But the equator, if you think about the equator, it doesn't really matter how the Earth is tilted. The equator is always going to be close to the sun, right, compared to the rest of the Earth. So it's going to stay warmer there. And so it's that temperature difference that affects these winds. The first the hot air rising creates a region of low pressure. So hot air rising creates a low, what we call a low, so region of low pressure. And that sort of makes sense if you think about it, because the air, when we talk about air pressure, when we discussed atmospheric pressure, that was due to the fact that air actually has mass, right? And so we use that example of how, you know, we had like this chunk of air. I think I used this little thing here, right? This chunk of air that was like sitting on my shoulder, and how, I can't remember how many pounds of pressure we said the air is exerting, but we don't feel it because there's also air inside of us that's pushing back in the opposite direction, right? But if hot air is rising, it makes sense that the pressure would be decreasing, right? That it would be low because the air is going up instead of weighting down, right? So the hot air rising creates a low, a region of low pressure, and the opposite happens with cold air. When cold air sinks, get a high pressure region. Or simply, we just call it a high. At the surface of the Earth, wind tends to blow from poles toward equator. So from the low region to the high region. Now this is reversed in the upper atmosphere because of those weird things that happen with the temperature, you know, as you go higher. But on the surface, this is basically the way that it works. It's going to get a lot more complicated than that, but we'll start with that understanding. So if that's all it was, we'd be good. It'd be like, okay, wind's always then blowing from, like in our case, in the northern hemisphere, it's always blowing from north to south, right? We've got cold up in the poles, and it's constantly blowing down to the equator, and we're done with our discussion of wind. It would be reversed in the southern hemisphere because the cold region is the south pole, and it's blowing up towards the equator. But of course, it's way more complicated than that, because if man had invented it, it'd probably be about that simple, but since God invented it and he's way smarter than we are, then it's actually a lot more complicated than that. So best we can understand, here's some of the other things that affect these wind patterns. Two major things that affect wind patterns. And they are changing air temp, and then something that we're going to talk about called the Coriolis effect. I'm just going to tack it on to the end here. It's not one of the main big two, but local winds also affect. big ones are the changing air temperature and the Coriolis effect. But so it's kind of like the climate versus the weather thing. Like those big items at the top are what define in general the way wind works. But just like, you know, it may be that in Southern California that it's normally sunny and dry, but sometimes they will have rainy days. That was the weather for that particular day. Sometimes the local winds can affect what's the normal wind pattern in a region. So let's talk about the first one. I'm going to erase some stuff. So, you got it? Okay. So this one, we're going to talk about the changing air temperature part first. So, because air moving from poles south, because air moving from poles to equator gets what? What's going to happen as the air is moving? So if the wind's blowing from the poles towards the equator, that's the normal behavior. What's going to happen as that air is moving from the north, say the North Pole in the northern hemisphere, south towards the equator? What's the one thing that we know is going to be different, or is going to happen to the air as it moves down? What's different between the poles and the equator? What are we talking about? The primary difference. You think of the North Pole, you think of what? Versus the equator. Huh? You can say it, it's okay. We'll only laugh a little bit. Nah. What is it? We like to laugh anyway. What did we say? The poles we think of as being what versus the equator that we think of as being. What's the main distinction? Do you want to go hang out at the poles? No. Why not?
It's cold.
It's super cold, right? So the poles are really cold. The equator's nice, right? People love to go to the Caribbean because of the weather being so nice there. So you can like always go swimming and things like that. Although the one time we went on a Disney cruise to the Caribbean, and it was cool. We got to watch the Pirates of the Caribbean on a Disney boat in the Caribbean. How many people can say that? I watched Pirates of the Caribbean in the Caribbean, right? But we went in February, and when we got to Disney's private island and we went into the water there, it was freezing. The water like literally took my breath away when I went down into the water. So we didn't actually get to swim when we were there. It felt great outside, but the water was super, super cold. But anyway, when you move from the poles to the equator, what happens to the air? It gets warmer, right? So that because the temperature is changing, as you move from the poles to the equator, it gets warmer. As air heats up. So we have this cold air that's moving from the poles to the equator. What did we say cold air does versus hot air?
Cold air sinks.
Cold air sinks. So we got this air that's moving, it's sinking. But as it's moving towards the equator, it's getting warmer and warmer. So what do we expect is eventually going to happen? It gets warm enough that it starts rising, right? So because of this changing air temperature, it's not just that it goes from the pole down to the equator and just blows that way. Because it warms up, it turns out at some point it gets warm enough that instead of sinking, now the air begins to rise, okay? And so as air heats, it begins to rise. In the northern hemisphere, gets warm enough to rise at about 60 degrees north. So that's the latitude, right? As the air is blowing from the North Pole down towards the equator, when we hit about 60 degrees north, then the air at that point has gotten warm enough that it's going to begin to rise. So let's see if we can see where that is on our globe here. So 60 degrees north is up here. Am I in the camera? Yeah, okay. So that looks like it runs through Russia and Canada. So somewhere in Canada, about the middle of the Hudson Bay in Canada, like the southern end of Alaska, actually. So the very bottom of that state is about where the air gets warm enough that it begins to start rising. And when it rises, as it rises, the reverse starts happening. And so what we see is not that the air just blows from the north down to the south. It starts blowing down to the south, but then when it heats up, it reverses and goes back towards the north. And so you kind of have this cycle as the air is coming down from the North Pole. The reverse, of course, is happening as the air is blowing up from the South Pole towards the equator. All right. We also see that the opposite happens as warm air from the equator rises and heads towards the poles. So same kind of thing happens. It's warm, it's rising, it starts heading towards the pole as it goes. If again, just thinking about the northern hemisphere, as it goes north, it starts getting cooler, and eventually it's going to get cool enough that it sinks, right? And so you get this cycle that's happening as you go from basically 0 to 30 degrees north or 0 to 30 degrees south, as the air is moving from the equator to the poles. And then you've got this area that's at 30 and 60 degrees on our latitudes, where because you've got these two systems that are doing this reverse thing on each end, then it gets all mixed up and does this reverse thing as well. So when you get finished writing that down, there's a graphic I want you to look at the top of page 168 that tries to sort of draw these loops to show you what's going on. So you can kind of see, just thinking about the North Pole, you can see how that cold air is sinking and heading towards the equator. But like I said, when it hits 60 degrees north, it's gotten warm enough that it begins to rise. And so then it returns back to the pole, so you get this circle up at the top. From the equator up to 30 degrees north, same kind of thing happens. You've got this really warm air that's rising and trying to go north. But then when it gets to about 30 degrees north latitude, it gets cool enough that it starts sinking and it circles around and comes back down. And so you've got like sort of this reverse pattern that happens in the middle there between 30 and 60 degrees north latitudes. Again, because it's being affected by what's happening above 60 degrees north and what's happening below 30 degrees north. So you've got these weird patterns, weird wind patterns due to the temperature change, the temperature difference in those regions. Does that make sense to you guys? You guys see why that might happen? Now notice he says in figure 7.6 that this is an approximation because there's more to it, because we haven't talked about the other big factor that is affecting our winds, and that was the Coriolis effect. All right, so we're going to give you a definition of that in just a minute. But before I give you a definition of that, we need to understand something about the fact that the Earth is rotating and how that affects the speed of things at different places on the Earth. All right, so how do we determine speed? Speed is a measurement of what? Like if you're driving in a car and you're going 55 miles per hour, right? So the unit on there gives you a hint as to how we define speed. We define speed, or rate is another term that we use for that. Speed is distance over time, okay? Or in a math class, like I said, you'll usually see it as rate is distance over time. All right? And the way that I always remember that formula is I think about my speedometer in my car. If I'm going 55, it's 55 miles per hour, right? Miles per hour means miles over hours. And that's how we calculate that. So if I drive 60 miles to get to a destination that takes me exactly an hour, then I drove on average 60 miles per hour to get there, okay? So if you think about that, when you consider the Earth rotating, all right? Let's say you're standing. Oh, it's still there. Oh, thank you, Lord. Let's say we're right up here at the North Pole, okay? And I'm standing right here at this point on the Earth as the Earth rotates around, all right? How long does it take me to go from here, all right, all the way around and get all the way back over here again to the point that I was before? How long does that take me to do that? In other words, the Earth rotated around one time and brought me back to my original position. How long?
A year?
No, that's how long it takes for the Earth to go around the sun. How long does it take the Earth to rotate around one time?
24 hours.
That's 24 hours, right? That's why we have day and night, is because of that. So if I was at this point, this is up at the very top of Russia here. Let's pick a point in Greenland. So this is Greenland. I don't know the names of any of the places here. I can't read it. It's like it's in a different language. Oh yeah, because they don't speak English. So we'll just say Greenland in general. I'm standing somewhere in Greenland here, right in the middle of Greenland. And so I rotate around. So if I were to take that circle there that's formed all the way around the Earth at that point, let's say I took a thread, a string, right? And I cut a string so that it matched that circle exactly. And then I took that string and I laid it out on the table, all right? And now I'm going to do the same thing down here in Georgia where we are in North America, right? And I'm going to go all the way around. How long did it take me to travel that distance down here in Georgia? All the way around one time as the Earth rotated. Not a trick question. How long did it take me to get from that point all the way back around? 24 hours again, right? The Earth takes 24 hours. But let's do the same thing. I'm going to take a thread again, and I'm going to stretch it from here all the way around the Earth to this side, and I'll lay it out on the table. Are the threads the same length? Is the distance around the Earth from here all the way around to here the same length as the distance from here all the way around to there? It's not, right? This distance here is much shorter, about half the distance that it would be, maybe even less than half the distance it would be for me to go here all the way around, right? So the point is, both of them, it took them 24 hours to go all the way around that circle, right? But one of them went around it one of them covered a lot less distance than the other one did in that 24 hours, okay? So what that tells us is that if I'm up here, the speed at which I'm moving around is going to be less. I'm moving at a slower pace because it took me 24 hours, but I covered less ground, right? Than this guy down here who also took 24 hours, but he covered way more ground than the other guy did in 24 hours, right? So his speed was much quicker. So we have to understand that concept in order to understand this idea of the Coriolis effect, right? If you're on this latitude, down here in North America, you're traveling faster than someone that's up in Greenland or near the North Pole. All right, does that make sense? It's because of the way that we define speed, right? One person travels a greater distance in the same amount of time than the other person does. So we need to understand that. That's important. And Again, this is the other major factor that affects, this is point number 2, Coriolis effect. And so understanding that, what the Coriolis effect, let me give you an actual definition here. The Coriolis effect is the way in which the rotation of the Earth bends the path of winds, sea currents, and objects that fly through different latitudes. All right. This is a factor as you go between different latitudes because the Earth is moving at a different rate at those different attitudes. Hey, Jonas is home. Got it? Yep. So he uses this example in the book of firing a missile, all right, from like the north towards the equator, and then doing the reverse. And so I'm gonna write this down just to kind of help you, because I think it'll be good for you to have in your notes. And I think there's a question on the test that's related to this as well. But we're gonna talk about it after I write it all down. Just make sure it makes sense. So if fired missile. Fired missile from North Pole to equator would bend east which is the direction of the Earth's rotation. Oh, I'm sorry, I said that wrong. I'm thinking through it in my mind. I'm like, wouldn't it be west? I'm sorry, guys. Would bend west. Since ground below is moving faster to the east. The direction of the Earth's rotation. Okay? So he's got this picture in the book. Did you guys already get that written down? Wow. So you corrected my mistake and fixed it while I was correcting my mistake. So you guys aren't slow, it's just that I'm saying it and you actually beat me that time, right? Whenever I had to correct my own mistake. Nice, all right. So if we fired a missile right? We're up here in the North Pole. We fire this missile. It's coming down here. We're trying to hit a point like down here around the equator. And so we fire this missile. So the missile's up in the air, right? I shouldn't have drawn it curved. I'm trying to show you that it's in the air. But what's going to happen is this point, let's say we're aiming at this point. If I just aim directly at this point from the North Pole, remember the North Pole's moving slower, right? This is moving faster. And so by the time the missile gets down here, this point is actually going to be over here, right? And so the effect of the missile is that the missile actually bent that way, all right? So because the Earth is moving faster down here towards the east, remember this is east, this is west. The missile bent towards the west because this point down here was moving faster and it moved along, all right? Now the opposite's going to happen if we fire it from the equator, right? So here's our equator, and we fire a missile to the north. Well, because the north is moving slower, and this part's moving faster, as we fire it, it's going to like slingshot it out that way. So it's going to bend towards the east if we fire it from the equator to the north. So the point is, so the reverse happens. Let's see, if fire from equator to north, pole missile will bend east, since the point of origin is moving faster. All right, so it's going to bend that way. Again, this is east. This is west. So the point is, if I have a point up here that I'm trying to hit, and I'm firing my missile, I mean, they literally have to do this when they have to do the calculations for this because of the rotation of the Earth. I have to fire my missile to the left of what I was aiming for. In other words, I have to fire it northwest because I'm expecting it to curve back around to the east, bend towards the east, in order for it to hit the target that I was aiming for. All right. So airplanes would have to think about this as they're flying, right? But it also affects the winds. So that's what the Coriolis effect is all about. Is the fact that these things are bending based on the difference in the speeds on the ground. Okay? Does that make sense to everybody? Yeah? So there's one other piece that I said can affect it, and that's just the local winds. And so there's a diagram that talk about sea breeze and land breeze on page 171. And so just note, remember, local winds can cause normal wind patterns to change. There could be local factors that cause it to behave in a way differently than we would normally expect it to behave, based on the temperature differences or the Coriolis effect. And so there's a section there's this figure 7.10 that talks about sea breeze and land breeze, and so it's kind of interesting. And I've never like paid attention to this to see if it's so. So I got to try this next time I'm on the beach and just verify that this diagram is correct. But it makes sense based on what we've learned. Land heats up and cools down faster than water. Okay? That explains why it was so cold when we were in the Caribbean. Even though the temperature was nice outside, the water was still freezing because it was taking longer for it to warm back up, the water to warm up. But so because land heats up faster, the weather on the land is warmer than the water when the sun's out. And so you can see that diagram there, that the warm air is rising and the cool air is causing this low pressure. The warm air rises and causes a low pressure on the land. And so what happens is you get this cycle of air where the wind is always blowing from the water onto the land during the daytime. But during the nighttime, the reverse happens because the land cools off faster than the water does. And so the warm air is rising out over the water now during the night, and the cool air is falling over the land. And so you get a land breeze instead of a sea breeze, where the breeze is always blowing from the land towards the water. So I got to check that out next time I go to the ocean. All right, you guys can help me check that too. You can send me an email one day and be like, Mr. Walker, we verified that it's true, or an email that says, he was totally wrong. I was standing on the land and it was blowing in the opposite direction. All right? I suspect though that he's right. So last thing I want to talk about is air masses, and then I'll let you guys go. And what is an air mass? And this is the stuff that you hear meteorologists talk about all the time if you listen to a weather report. This is a large body of air with relatively uniform pressure, temp, and humidity. And so these air masses, they tend to move, they tend to stay together and move as an entire unit. And we divide them into three basic types. And there's a diagram, or there's a drawing on page 172 that shows the three types. We have Arctic, polar, and then continental. No, I'm sorry, tropical. Right? As you'd expect, both of these are cold. This is warm, right? It forms over ocean. If this air mass forms over an ocean, we say that it's, we put maritime in front. So just think of marine, right? Like marine life, it's life in the ocean. So M-A-R-I at the beginning of that. If over land, put continental in front. All right. So this one's usually wet. This one's dry. Right? Makes sense if it forms over water that there's going to be a lot of moisture in it. So if the mass is maritime polar. And so what they usually do is they put the M, first word, when they abbreviate it, the first word is lowercase, and then the first letter of the second word is capitalized. So MP. What would you expect this air mass, how would you describe that air mass based on the terms that we know? The little bit of details that we have. Maritime polar. What would you expect it to be?
Wet and cold.
Yeah, wet and cold, right? And so we could make another one if continental tropical or CT. We can say it's warm and dry, right? So you got these big air masses, right, that are moving along the surface of the Earth. That like this picture that you see them moving around here on 7.11, that figure there. On the next page, figure 7.12, you see these two air masses colliding, right? And so when two air masses collide, generally something happens, right? There's some sort of weather event that occurs when these two collide with one another. So I've got 4 quick definitions of weather fronts that I want to give you, and then we'll be done for the day. So we give you, first of all, a definition of a weather front. So weather front is a boundary between two air masses. Did you get all this stuff copied down here? Okay. There's 4 types of weather fronts that meteorologists use. And that's just the term we use for a weather scientist. Scientist that studies the weather. So we have a cold front. And cold air mass moves into region of warm air. When this happens, we usually get the most severe weather. So usually causes most severe weather. Like I said, when these two systems collide, things are not going to stay nice. And so when the cold front moves in to take over, we usually get really bad weather. The warm front, on the other hand, still brings rain with it. So this is the opposite of warm air mass. Enters cold air region. But it's a really pleasant rain usually. Produces long, lighter rain. So the rain lasts longer, It's not like this big eruption, violent storm kind of thing that blows through quickly. It's usually a long, lighter rain, so it's like a great rain for your lawn and your flowers and all that sort of stuff because it's not destructive, but it just kind of sits there and saturates everything. I'm going to take a break a minute and let you guys get caught up before we talk about the stationary front. So when you hear stationary, what do you think that probably means? You guys are pretty stationary right now, right? What do I mean by that?
Calm.
Huh? Calm? Yeah? And you're not moving, right? It's like you guys are working me to death. I'm having to move around up here and doing all the work, right? You guys are just doing this little tiny little, just mostly stationary, right? So stationary, that's what it has to do with. Like a stationary bike is a bike in your home, right? Where you stay in one place and you can work out without moving around. So in this case, neither air mass moves. They hit up against one another, but they just both sort of stay there, right? Nobody kind of wins the battle. And so whatever the weather is, it sits for a while. Sits for a while. And then finally, an occluded front. And this is so like for the first two, sorry. So for the first two, you've got like air masses moving in the opposite direction, right? So they collide with one another and one of them wins out, right? And kind of the same thing here. It's stationary, they come up against one another, but one's not really stronger than the other, so they just sort of sit there for a while and nothing happens. But in the case of an occluded front, that's when you have like both air masses moving in the same direction and one like catches up with the other and overtakes it. Okay, so that's what's kind of unique about this one. Two air masses moving in the same direction. All right, collide. And what usually happens is the cold overtakes the warm. So cold air mass moves faster than warm. So since they're moving in the same direction, initially what might happen is you get a behavior that's more like a warm front, right? Where you get that nice light rain that's real enjoyable. But because the cold front overtakes the warm air mass, that it ends up turning into really nasty, severe weather. Seemed nice and pleasant to start with, and then it gets bad. And you know, as you're reading it, they've got some nice little drawings in the book, and they'll show you like the type of clouds that are typically involved in like when these masses collide. the type of clouds that you generally see, cumulonimbus or stratus and nimbostratus clouds, things like that. The particular front will produce different types of clouds. Okay, but the main thing that I want you to know is what the stuff that I've jotted down here. So I'm not as concerned about what kind of clouds are there. Just want you to know that this is severe weather. This is a light, long rain. This just kind of sits, the weather just stays like it is for a while. And this one starts off light but turns severe. Okay? Make sense? All right. We're done with 1 minute to spare. Perfect.